So this is a bit of a provocative starting slide with the dead zone, but I couldn't resist because it's such a great, it's just a great place to start. What I'm going to do is set the stage for some really interesting stuff that Pete's going to talk about specifically on Lake Erie and the Lake Erie watersheds. But we've been doing a fair amount of work on this particular issue of relating agricultural nutrient sources and its impacts on coastal and Great Lakes systems for a while. And I'm going to start talking a little bit about the bigger picture. We can talk about nitrogen as well as phosphorus in this case, a little bit about the Chesapeake Bay, the Gulf of Mexico, and then move it over to Pete to talk about the details on Lake Erie. So this issue of nutrient over-enrichment of coastal systems has been studied for quite some time now. And this is a map showing the United States, showing where this is a problem. Anything that is yellow, orange, or red is identified as a problem in these coastal systems, so showing symptoms of eutrophication, overgrowth of algae, dead zones, hypoxia, and the like. So it's a nationwide problem. It's also a problem at the global scale. This is an analysis that was done recently looking at areas of impacts from nutrient overloads in the coastal ocean, over 400 known areas of hypoxia, or hypoxia is being very low oxygen concentration, covering almost 250,000 square kilometers around the globe. So this is a very large problem that's persisting in this country and nationally. And agriculture is one of the players in this game. There's no question about that. Point sources are other point sources from treatment plants and others are also important. But in many cases, agriculture continues to be one of the sources of nutrients going into these systems, where we need to be paying more attention. If you look at over the long time scale and globally, if you look at the amount of reactive nitrogen that is going into our system, it can come in from burning fossil fuels. That's the line at the bottom. Nitrogen-fixing crops are bringing nitrogen into the biosphere, and that's the second graph there. But industrial fertilizer, inorganic fertilizer, the green revolution that we're experiencing, is the main source of nitrogen going back into the biosphere. And you see how this has changed over time. And this is just a correlation. It's not necessarily causation. But if you plot on top of that, the cumulative number of systems reporting hypoxia in the coastal environment, you can see there's a very strong relationship going on there. And this has been shown over and over again in individual places. So if we back up and we look at, well, what's this relationship between nitrogen and phosphorus on the land, and that nitrogen and phosphorus going into the environment? This is one of the works that were done early, looking at the relationship between the net input of nitrogen to a watershed and then what comes out of that watershed. So this thing called NANI, which is net anthropogenic nitrogen input. It's all the input of nitrogen into a system minus the nitrogen that comes out of the system. So the nitrogen comes out in crops, in other areas. If you plot the amount of nitrogen leaving that system in the rivers going into the water bodies versus that net anthropogenic input, and you look at it at very large scales here, you can see each one of these dots here represents the Mississippi Basin or Northern Europe or the northeastern United States. You see that the slope of this curve is about 0.2. And so what that says is about 20% of the nitrogen that goes into a watershed flows out from the rivers out into the ocean in this particular case. If you look at this at a somewhat smaller scale, and these are now, each symbol here are sub-watersheds along the eastern coast. So it's the Delaware River into the Chesapeake Bay, the Potomac, the Rappahannock, and those sort of systems. Again, the slope is 0.26, so again, about 20-25% of the nitrogen that goes into these watersheds is going out through the rivers into the system. Similar work has been done here in the Great Lakes region, looking again at nitrogen, and these are Lake Michigan watersheds. In order to make these relationships even tighter, if they include a hydrologic effect, and that is the amount of rain and water flow in the area, you still get this very strong relationship between how much nitrogen goes into those watersheds and then how much goes out of the watersheds into Lake Michigan. So again, there's a very strong relationship there. And this also holds for phosphorus. This is fairly new work looking at the top row is Lake Michigan, the bottom row are the watersheds around Lake Erie. And again, very strong relationship between how much phosphorus is going into those watersheds and then how much is flowing out of those rivers into the Great Lakes. And so again, the strong relationship between what happens on the land and what ends up in the water. was becoming more and more interesting, particularly if you start looking at phosphorus, because phosphorus doesn't seem to be as uniformly consistent as nitrogen. You saw most of those graphs I showed you about nitrogen, that 20% number was pretty consistent. But if you look at phosphorus, and you look at the relationship between phosphorus going into that watershed and phosphorus coming out of the watershed, and you compare the Chesapeake Bay, Lake Michigan, and Lake Erie watersheds, the slope is changing dramatically. And interestingly, what we're seeing is in the Lake Erie watershed, there's a higher fraction of what goes into that watershed of what's coming out than in the other systems. So something is different in the Lake Erie watersheds, and Pete's going to be talking quite a bit about that. So I've got just a few slides here to show in the Gulf of Mexico and the Chesapeake Bay, and then leading to Lake Erie, something very strange is happening across the board in these systems, and also in systems across the globe. This is the region of hypoxia, the dead zone in the Gulf of Mexico from 1985 through 2007. As many of us know, it increased around in the mid-90s, and it's now hovering around this 18 or 20,000 square kilometers. So it's a very large area. When we start looking at the relationship between the size of that dead zone and the amount of nitrogen going into the Gulf of Mexico, at first we saw what we'd expect, and that is, as you put more and more nitrogen into the system, you're getting larger and larger dead zones. But if you look closely at this, those yellow dots actually come from years before 1992. The blue dots are after 1992. And what we're finding here, and again in other places, is that the same amount of nitrogen going into the Gulf, let's say 6,000 tons, you're getting more hypoxia now than we did earlier. The system has become more sensitive to the nitrogen loads. If you look at the Chesapeake Bay, with the same sort of thing, this is the time course of the hypoxic volume in the Chesapeake Bay, driven very much by the nitrogen load. And if you plot that area versus the nitrogen load into the bay, again, you get this relationship between the two, but a very different. You're seeing a much more sensitive system now. This is now the post-1986 than we were before that. So the same amount of nitrogen going into the bay is creating a larger dead zone now than it did in the 70s and the 80s. So the system has somehow shifted to become more sensitive to this load. So something's happening, and this is actually happening in a bunch of other places. So how does this relate to Lake Erie and to the work that Pete's going to talk about? Well, as most of you know, Lake Erie was a big problem. Right? We declared it dead back in the 60s. If you look at the area of, this is now anoxia, which is just a more extreme version of hypoxia. If you look at that area of the bottom water that's anoxic over time, you can see from the 1950s through the 1970s that was increasing, and that was because more and more phosphorus, in this case, was going into Lake Erie, causing this larger and larger area of hypoxia. But then in the 60s and 70s, with the innovation of point source control and ban of phosphates and detergents, we got lower and lower phosphorus going into Lake Erie. And as we'd expected and as we hoped, the size of this anoxic zone in the central basin of Lake Erie decreased, and that's the second half of this curve. It was decreasing pretty substantially during that time period. But it's back. Phosphorus loads have not changed in the last decade or so. They're still as low as we had originally wanted them to be, the total phosphorus going into the lake. But the size of that dead zone in Lake Erie has increased, and it's now back to what it was like back in the 70s. So something strange is happening in and around Lake Erie. Even though total phosphorus loads are still the same, the amount of hypoxic area in Lake Erie has now increased, and we're not quite sure. So this is where I'm going to turn it over to Pete, and he's going to give you at least one explanation for why we think it's happening, and then some ideas about what we ought to do about that.